probably skip the first part of the talk. So I understand that I should stay close to the laptop because of the voice. So, yeah. So. Okay. Thanks for coming. So this is a piece of research that really started just before the pandemic hit. So in February 2020, that was, I think, the last physical meeting at the RSS for a discussion paper. And so that is something that arose from our discussion contributions afterwards. And so I wanted to apologize. It's a fair bit more theoretical, I suppose, at the moment. I have a gallery of examples of applications towards the end, if you're interested. So, so this type of research has also been applied to networks of river discharges, looking at airport traffic delays, looking at currency exchanges, but that is not going to be the main part of the talk. I would have liked to be a little bit further down the line with another piece of research on spatial extremes I'm currently working on with my colleagues, but we haven't quite a data example there where I would like it to be. So, so I decided to go back to this piece of research, and I hope you find it interesting anyway. So this is a joint work with Sebastian Engelke, who was one of the authors of the RSS paper, and Yevgeny Ivanov's. So so for some reason the errors don't work. Did I somehow, okay, if I click, no, yeah, that works, thanks. So I'm going to start with some motivation, maybe a journey, a direction from which I've been coming to this topic. So it's going to be about multivariate extremes and graphical modeling. And so in order to get there, I will have to say a few words on both things. First, multivariate extremes, and then graphical modeling. The backbone of kind of graphical modeling in multivariate situations is the concept of conditional independence. And it turns out that we kind of need to reinvent it for this set. So it's not quite clear what it means in this context. And I think we have some quite interesting results on undirected and directed graphs with the notion that we found. And I hope I can convince you towards the end that it seems quite natural, and somehow I think that we have found a natural concept to deal with that. So I think that's probably going to be very boring for many of you, and you have heard that already several times. So typically in extremes, they're interested in trying to understand something about risky regions that are fairly, well, not so close to your data anymore, maybe even going beyond the data, or maybe at the boundary of data. And typically you ask questions, or what is of interest is, what's the probability to lie in such an area? Or conversely, if you have a given probability, what's the level basically? What would the region look like? Where would I have to set those boundaries? And there are many, well, classical areas of applications. I think there. So yeah, so there are more areas now. So what's guiding this extrapolation into those regions? Well, you can't use empirical estimators because you don't have data in that region. And it's also a flawed approach to use parametric models where the fit is dictated by the bulk of the data, basically. So, and the idea behind extremes is using kind of regularity properties for the kind of extrapolation, and they take different forms. So typically, one of the starts of the development is, well, instead of looking at central limit theorems, you look at limit theorems at the boundaries. And it's fairly well known, the famous Fisher-Tippett type theorem, that if you replace sums with maxima, that the result is going to be satisfy stability properties. If you take limit laws for maxima, your distribution is going to be mass stable. And so this, these distributions are well known and classified. In univariate extremes, it's just a single parameter that classifies those. And but you could so also come from different directions. Doesn't have to be a limit theorem for maxima. This is just a start historically, probably for the journey, but you can also, so the vanilla methods in extremes are looking at either threshold exceedances or at block maxima. They just inspire different kinds of methodology, but which are theoretically, at least in the IID setting, equivalent, basically. So you've probably seen already data analysis of this type, where you either look at blocks in which you look at the maximum, or in the peaks of a threshold case, the limits. Basically, you have models, generalized pareto distributions for those. The univariate limit when you choose threshold is going to be plotted approximately pareto distribution, and just a different way how to select the kind of data that you want that you select as extremes. And behind those two, there's something maybe even stronger, at least in the IID setting. And you can also start to tweak that from there. Behind both of those limit results, there is a Poisson point process limit. So if you type data and more data fly in, basically, and you suitably normalize them in time and in the time and scale and location, then you converge to Poisson point process. And both of the limit results for maxima and threshold exceedances have been, you can derive both of them basically from there. So what's happening in the background, or maybe it's a bit more insightful. Okay, let's just see how I can, I think I need to stop share in order to bring that video in, and then I'm gonna, so let's see, escape, or no, escape is not the right thing. Okay. Yeah, so, and then I can share this, I suppose. Share screen with this bit, yeah. Yeah, thank you. And just wanted to show you what's behind this. So, so as more and more data come in, basically the number of points in a certain interval are going to stabilize if you normalize correctly. And at the same time, you also see that the distribution should, in principle, stabilizing. And this is just an example where I just did that for an exponential distribution, but it applies to wider range of settings. And this kind of stability is the one that usually is behind most statistical methodology in the area. It's just, I think it's kind of illustrating the point. So usually you use this kind of regularity property in order, in both cases, essentially, if you do that, to guide your extrapolation. And from which most of statistical methodology is derived from. So I'm gonna share now the other part again. So that is presentation. Okay, yeah, so there's also a nice paper by Axel Bücher and Chen Zhou recently in Statistical Science, a horse racing between block maxima and peaks over threshold approach, where they compare the two against each other, disadvantages and advantages. I think that's quite good that some people took the time to evaluate that. That is, so, okay, so, yeah, so, but actually I didn't want to talk much about univariate extremes, as important as it is. Both is important. The univariate extremes, the marginal distributions, and also the dependence between different components in a vector. I'm now taking the approach, I'm hugely simplifying right now. I'm going to leave the situation that I have only, or I'm going to look more at the situation that I have actually, situation where I have regular variation. I'm only looking at heavy-tailed marginal distributions now. And but much of the theory actually carries over. So in, at least from a theory point of view, if you look at maxima component-wise, or at threshold exceedances where you condition on exceeding that the norm of a vector exceeds a large threshold, you can marry that again with each other, basically, from a theory point of view. You can translate one limit result again into another, and also the point process limit in the background. Except that this time, maybe I should point it out here. So the component here is going to be a measure. There was a measure beforehand as well that it was homogeneous, but this time you have a measure that lives on the upper orthant. So I'm going to focus now on positive random vectors. And so basically beforehand, you have just one direction. Now we have several directions. So dimension, this measure is going to live here on the upper orthant. So in higher dimensions, you could imagine this measure is going to live somewhere. And this is the object that summarizes the dependence between the different components. Depending on how that measure looks like, you get understanding how different components in extremes are dependent between each other. So because it appears here in the max stable limit in the exponent, this is often called exponent measure. But it also appears if you look at threshold stable limits. So if we condition, for instance, on the supremum norm being large, this limiting measure is going to live on space where we take out, giving one sphere with respect to supremum norm. And so the multivariate pareto distributions live on such a space. And depending on which components you condition on being large. So one could also replace this result with another norm, and one would get the same result. These kind of things are fairly, say, well known in the community, but I think it's rarely written up in a way that you have all kinds of equivalences together. And one resource that I particularly like is Lévy. They do it in a functional setting for, say, continuous data on a compactor. But I think they've done a pretty good job in summarizing different ways of looking at limit theorems in, say, in their case, it's a spatial context, but you could also interpret it in multivariate context, which is actually easier than that. But the one thing that I want to keep track of is that measure that appears in every limit here. So we have this exponent measure, or some people would call it probably Lévy measure. So if you're more on a probabilistic side, you would say, okay, this is a infinitely divisible distribution in some sense, and then it can be interpreted as some kind of Lévy measure. So go back, forward. So how do these measures look like? Well, they are locally finite once you step away from the origin. So the Pareto model lives here, but the measure actually lives on the whole upper orthant. And once you get close to the origin, it explodes. This has to do because you have lots of data in the bulk, basically. Yeah, so that you neglect. That's why it's going to explode. It's also to do with the stability that you get after. So it's homogeneous, so it has to explode anyway. It doesn't have mass at zero itself. And if you're a probabilist, you would probably talk about it as a Lévy measure. But we should keep that explosion in mind, and also in mind that once you step away from the origin, it's not exploding, so you're going to be finite. Okay, and so any such measure that has these properties, not even necessarily homogeneous, are going to be measures that I'm going to look at in what follows. So these are my motivational measures, but I don't necessarily have to have homogeneity. So all that matters in what follows is that if I step away from the origin of finite and explode in Multivariate extremes. So there is a huge body of literature in multivariate extremes about multivariate extremes models, more than 30 years actually. I mean, so some of the most prominent models nowadays have actually been invented in the late 80s, and they're still, well, they have entered textbooks over the last decades. And but one problem is that very often these models don't really have a natural way to scale to higher dimensions. And it's sometimes difficult to interpret the parameters in them. And so there is a lack of models that somehow have also structural insight, and from which you can, from smaller models, maybe click them together to larger models, some kind of toolkit to do that, and in an interpretable way. So, and so since some time, there's research into trying to embed meaningful sparsity structures. And so often sparsity structures are approaches where you try to decompose a signal into, say, orthogonal components. This is something, some natural way that is interpretable. Or another way is looking at not independence, but at conditional independence, which leads to the literature of graphical models. And that's what I'm going to focus on in this talk. So basically, I think my own first encounter with the topic was in a joint research with Yannis Papastadopoulos, 2016, where we looked at max stable distributions and tried to find out how can we interpret conditional independence within such vectors? Is there a natural way how to do that? But we didn't quite succeed. I think it was a negative result that we had at the time. And instead, there were two lines of research that were more successful, that really tackled the problem much better than we could imagine at the time. And so maybe let's just recall this kind of impossibility theorem. So what we found is that whenever we have a positive continuous density in such a vector, and we have disjoint subsets of our index set, then conditional independence implies already independence. So we had a proof for that. And this is a very unnatural thing somehow. It really doesn't lend itself to any meaningful incorporation of sparsity structures in most of the most well-known models. So we often say that the Gaussian model in extremes is called Hüsseler-Reis distribution. And so it wouldn't work for that phrase. That would exclude the Hüsseler-Reis distribution from even being considered for modeling of graphical structure. But so we sort of had deal done, so it's not meaningful. We didn't have much hope.
Just one.
Second?
Just one.
Yes, only this direction. So yeah, exactly. So yeah. So, but instead, so there are two other lines of research, so one of them is started by Claudia Küppelberg. So she started to look with her team at structural linear models. So, so they start directly from a graph, and then so each node corresponds to one component in your vector, and then you have weights assigned to those positive weights assigned to those edges. And so you can write down directly these structural equations. So at each node, in addition to, if you walk along these paths here, in addition to these weights here, you collect each time a new noise variable, basically. So each of these nodes. So these are these ZIs, or yeah. So, and on the other hand, there was another line of research that was discussed at the 2020 meeting, looking at these pareto distributions that arise there, and instead of looking at this strange space where you take out this part here. So the approach that Sebastian and Adrian looked at is trying to look at spaces that are actually product spaces and where it would make sense to post the measure into products. And this was successful, and led to a new notion of conditional independence for Mr. Rice's graphical models. And this corresponds to density factorization of this generalized Pareto distribution in the multivariate case. So, so there were two lines of research that found ways to meaningfully do this, basically. But of course, there are always also sometimes obstacles that haven't been quite overcome with this approach. On the left-hand side, the max linear approach has this struggles in the sense that it's not very realistic. So these measures basically that you get from these max linear models, they live on rays through the origin, basically. So they do not really resemble data very well. So and one has to give them some additional tweak in order to fit them to data in a meaningful way. They're not, they don't really lend themselves very natural frequencies. And the threshold approach here on the other side, this had the problem that you can't have independent components. So the graphs always need to be connected. And this was imposed by this kind of density decomposition, or even the fact that you have to have a density and you do not allow mass on these sides here. So, and this, there are these two approaches. And so this was a starting point for our research, because we were thinking about, okay, how can we overcome this? So can we maybe define something? So if you go back maybe to the previous page, okay, so, no, it worked, okay. So if you remember, here, this is the maxima approach, this is the threshold approach, but what is in the background is the Poisson process. And what connects them is this exponent measure that appears in all approaches. So can we maybe go back a step and say, okay, let's not do it for the maxima or threshold approach, let's really try to do it for the exponent measure directly. Can we do this in a meaningful way? And and if we want to have graphical model, I need to say, give some further background actually that right now. The backbone of these is the notion of conditional independence. So if we want to have a notion of graphical model, beforehand, we need to clarify what conditional independence means for us. So here is something that I learned from the book of Lévy. So there are various different ways how to encode graphical models in a setting where you have a graph. So imagine that we look, for instance, at a graph and each node corresponds to a random variable. Then we could, I'm not going through all those properties, but just to give an impression. So the graph gives us now a notion of neighborhoods, if it's directed, of descendants and parents and children, or these kind of relations are now there. And we say, for instance, that the pairwise undirected Markov property is satisfied for the probability measure represented by all the nodes, if for every non-adjacent pair of nodes, alpha is independent from beta, conditioned on the rest of the nodes. This is one way how one could encode the Markov. This is the undirected one. One could also say, for instance, if we go for the undirected global one, if we can separate, so if we take a partition of our graph, of our nodes, and we have for every situation where a set of nodes separates part A another set of nodes from part B, another set of nodes in the graph, whenever such a situation holds, that A should be independent from B given S. So if we have some kind of, so we know this for Markov chains. So if we have the present, condition on the present, then past, future become independent, basically. So this would be a separator set, and but in some situations, these properties are actually equivalent. So there are also theorems that tell you in some situations that they are equivalent. You can also have all those directed versions. So I'm recalling both of them because previously the Maxima approach by Claudia Krippelberg, that was more about directed models, and the threshold approach by Sebastian Engelke, that was more about the undirected approach. So this is basically these are the most common Markov properties considered. Okay, so before we can define graphical models, first we need to clarify what conditional independence means for us. And so we have now these measures that explode at the origin, but if we go away from the origin, we're finite. So the most natural idea that you could have is, let's do something with test sets. So typically, if we can't define something directly, let's try to think about what are meaningful test sets. And so we have this test set approach that, let's say we have a partition of our nodes. And so once we get away from the origin, we're going to be finite. So let's look at all product type sets that have mass. And if they satisfy conditional independence, and if that happens for all such situations, then we say that the measure itself satisfies conditional independence. So we look at all product from sets that are charged and which have finite mass because they are away from the origin. So we say that the measure lambda, that, so if the measure of lambda is going to live on such a space, but with several components in. So each component, each corresponds to one node in the graph, basically. So, and so we say that A is independent given C with respect to lambda if classical conditional independence holds whenever we go away from the origin. Does this make sense? So we have, so imagine, for instance, in R3. So now we have 3 directions. So we could think about graphs like this. Each direction corresponds to one node. And if we go away from the origin and say we take a little cube somewhere here, then we can take the measure lambda because it's finite. If we restrict it here to this cube, we can normalize it to a probability measure. And we can say, okay, now let's take a random vector that is distributed according to this probability measure. And now, because we have a product from set, it makes sense to require that can test. It turns out that this is seems a very natural way to do that, and that leads to some powerful concepts actually. So every feasible product from restriction of lambda results in classical condition. This is our requirement. Okay, so this is a definition. Okay, and I apologize, I need to introduce a little bit of technicality in order to formulate some of our results. So one thing that is probably very natural is looking at the marginal measure. So so if we wanted to restrict, for instance, just to 2 directions, then we can take the marginal measure. So we write for the subset of the nodes the margin here, and also the restricted measure when the other components are actually 0. So this is a different measure, of course. If we cite the measure and have also the condition, when we look exactly at the point where we are at the hyperplane. And we need some explosiveness assumptions, but essentially I'd like you to forget about these and just imagine, again, this explosiveness idea that we had at the start. So imagine any measure that explodes at the origin somehow. That will do. So one could be a bit more precise about these explosiveness assumptions, but these just, they're satisfied for all those homogeneous measures that we looked at the start. So, okay. Whenever you have test classes, first question is, can we reduce the test class and make our lives easier so that we have to test less? And essentially the answer is yes, we can reduce the test class. We don't have to test for every little cube. All we have to do is we need to test for all situations and just take out a slice from hyperplanes. So for instance, we don't have to test for all of these cubes or this. It is sufficient to look at all sets of this type where we can go an epsilon stride away from the edge. This is enough, basically. Then we will test it for all those other sets. And we need to do that for all directions. Or we can do that for all the conditioning directions, and in addition test that once we collapse our measure to the conditioning set, that then afterwards independent. Another question that one can have is, okay, usually these kind of conditional independencies are associated with density factorizations. Is that here the case as well? That was also the case in the previous RSS paper research of Sebastian and Adrian. And yes, it appears again, but one has to be a bit careful because now we allow mass not only in the open upper orthant, but also on the boundaries, basically. And we need to be very careful with those boundaries. So somehow, something that we learned is we have always this condition here, the independence once we collapse to the boundaries as an additional testing issue afterwards. So this is a condition that we carry always in addition to the density factorization. And the density factorization also needs to be checked when the components of the conditioning variables are different from 0. So where you
that's our generated. I check all the estimates. I'm confused. Is that the same as I just check all measurable sets anyways then? That some distinction that we're taking on the small. But I'm checking all the epsilons anyways. Isn't because
well, yes, in the homogeneous case, it's sufficient to just take one epsilon. Then it doesn't matter. So if your measure is homogeneous, you can just take any epsilon 0 and then it will automatically include. But you always need to take out an epsilon stripe and then test for the rest because then the measure is finite. Okay. I'm not sure answering the question. So
my question probably dumber than that. Checking all the epsilons, then isn't that the same thing as not considering the stripe being taken off?
Yes, exactly. But then in addition, we need to test the part that we've taken out. So we need to look at the measure when we restrict it to the components being 0 and check that always in addition to that. Because there could be mass on that space. This is something that we need to do in addition, but only for the conditioning components. It's it's taken us quite a while to find out. It seems natural in hindsight, but I think it wasn't obvious to us at the start. That's right. Yeah. Or maybe just to develop a bit of intuition. So we have a notion of conditional independence, but what does independence actually mean? So that was the thing that was missing first. in the threshold approach of sparsity. So independence, say if we have, let's maybe just look at the pictures. So imagine we have this plane here going through the 1 and 2 components, and the plane going through the third component. And if the mass of our measure is sitting exactly on these 2 spaces, then the 1 and 2 component is independent from the third component. So this is exactly characterizing independence in the setting. And this is something that is fairly familiar to people working in extremes. So when our exponent measure has mass on those axes, it's usually when we say that we have asymptotic independence between components. That doesn't mean that we can completely neglect this. Very often this just means that the model we're looking at is not the right one. So this was something that was missing before in the setup, and this is something that we can now characterize. And another point that I'd like to make is one has to be quite careful about. So if you have more than 3 components, quite complicated situations can arise in the setting. For instance, one could have a situation where the mass is sitting on such intersecting spaces. And in this case, for instance, if we collapse the measure to the in the 2 direction, then we would have the kind of cross, basically, right? If we look at the marginal measure. And in this situation, we know that 1 and 3 are independent from each other. So one has to be quite careful with taking margin of the situation. But one can also technically write that all down, and I think we found good notation in order to do that and keep track of these good bookkeeping devices for that base. But I think, yeah, this is a starting point to develop intuition around independence, and the part that was missing, and why we actually need the situation that we can have mass on different spaces. Otherwise, if you require a density in the space, you can't have such situations, and this explains why you couldn't get graphs that were not connected. So they just couldn't appear because this was missing previously in the research. So, okay, so let's see another thing, I think that's quite interesting. I said the density factorization is complicated because we always have to keep track of additional conditions. But if we modify the density in a certain way, if we say we take now, when we take densities, we need to take into account that we can have mass on the subbases. So if we take densities, we now need to take densities with respect to measures that have mass at the origin, basically. So imagine, for instance, you take the back measure and delta 0 mass at the origin as measure with which respect to which you take the density, basically. Then you would only have to modify it in a situation when you actually hit 0. And in this situation, you can actually recover complete density factorization. And we don't need to work with this additional condition. So it seems quite a natural object to work with this density, with this modified density, instead of the original one. So if we only take densities with respect to Lévy, it will work. But if we take Lévy, but in addition allow for point mass at 0 in each direction, then one can formulate quite natural density. So, okay, and so the one thing that people in the graphical modeling community care quite a lot about are these semi-graphoid properties, because they allow us to get a lot of things for free. Once one knows that these hold, one can easily derive relations between the different Markov properties. And one thing that we've been battling quite a lot with is the last property, the contraction property. And this is the only one that needs our explosiveness condition. So the other ones are quite easy because they just are inherited basically from the classical notion of conditional independence. But the one that, that took us quite long to understand is the last one. And that really needs this explosiveness assumption. This is where it goes. Well, I've talked a lot about conditional independence. I'd like to come back to graphical models in the end. So what have we gained, basically? So a few things at least. So just a quick reminder. Yes, please. Yeah.
And it's an extrapolation for those.
Apologies, I couldn't get the first part. So you've got
the in the back relation there. Then in that case, is it just regular?
No, it's not. No, it's not. No. So we've also been thinking about if we can incorporate the classical setting of having a probability measure on RD, but it's really different because we need the explosion basically for the session. So in some cases, yes, but we have also counter examples for that. So it's also capable. Thanks for the question. So yeah. So just thank you for giving the battery. So here quick reminder about the Markov properties. So what can we learn for either undirected or directed versions? So undirected graphical models. I think one of the results that we're quite happy about is that we can prove the Hammersley-Clifford type theorem. Well, I should say for decomposable graphs, these are graphs that one can construct iteratively by gluing a new graph to an old graph along complete separator sets. It's something, well, our proof has a recursion on this kind of situation. And so that's why it only works for decomposable graphs. But for those, something that, well, if we have such density, what we can show is that the measure is globally Markov, if and only if we have that our modified density allows for such a decomposition. So this is the entire modified density. And here the one for the separator sets. And here we go through all the clickers of the graph. So it's kind of reassuring for us because it shows that this modified density is the natural object to look at. So, kind of any further kind of research should also look at this modified density, and this is what we should be working with if we wanted to use that. So I think I'm time-wise still okay. Yeah. Okay. So and we need to look at it at all the points where it makes sense. So it looks quite technical, I think, but it really resembles the classical Hammersley-Clifford type theory. So we kind of recover that for the modified density. Then we can use, we can also follow a constructive approach. How can we construct from building blocks new models and glue them together? The one thing that was missing previously was that we could glue, for instance, independent models together in a certain way. And so if we, if we wanted to construct something that satisfies a certain conditional independence relation, we now have an idea how to do that. Basically, that's what I wanted to say. This situation, without really going into details how to do that, but yeah. So you can imagine those, different densities along those different subspaces, and we know how to construct the one here, for instance. So, and which kind of relations they have to satisfy so that we can glue them together. So for the directed ones, something that is otherwise quite well known is that directed global is typically equivalent of the directed local Markov property. And this is something that actually only needs the semi-graphite properties to hold true, all four of them. So, and so now we know also that for this kind of notion of conditional independence, directed global and directed local Markov property are actually equivalent. And finally, coming back to those max linear models that were studied from these graphs, if we type these structural equations, it's not very difficult to verify that how the exponent measure looks like, that's going through raised through the origin. One can actually write that down, and one can ask, okay, does this measure satisfy Markov properties? And it does. It satisfies the local directed Markov property with respect to its own graph, basically. That is reassuring. And it also satisfies the global ones if the noise variables that we have in the system do not have mass at the origin. Basically, that is in otherwise problem. So then it also satisfies the global. And yeah, so I think this is a maybe good. I'd like to come to basically the end of my talk and give you some conclusions. And so we have found this new notion of conditional independence that summarizes what's happening in two streams of research, and it seems to be compatible with both of them. It's definitely an extension of the Engelke and Hitz approach. And what this research shows is that some of the restrictions are not necessary at all. We do not need the existence of a density, and we also do not need homogeneity. Actually, it's important that we don't have a density, that we allow for mass on all those subphases through the origin, in order to have a more complete understanding of this kind of conditional independence. So it overcomes the key obstacle. We can also now have disconnected graphs. That wasn't possible before. So colleague just told me that they've applied it with their new statistical graphical lasso to a lot of banking data. And he said, okay, they've always asked back, yeah, but what are the components? So they were asking, they were more interested around the clustering of the different parts into different disconnected components rather than the strength of the actual components and the sparsity of the graph itself. So, and so it seems to be an essential piece that is reassuring to have now in the model. And so it bridges this max linear and Pareto approach, these kind of, say, vanilla approaches and extremes from which these graphical model approaches have, from which they arose. We have this special role of mass through the origin, and that's where the work sometimes gets quite technical. So I think that's also where I would expect take-up to be probably a bit problematic, unless you have ready software packages for it, and also probably a bit difficult to communicate. Meanwhile, I think there is already quite a lot of happening with the Lévy graphical models, but in principle, this research shows that one does not have to look at the Lévy graphical models. They are quite restrictive in some sense because they require certain symmetries, and so one can go beyond that actually with these kind of models. But one has to accept a bit more complication technically. And I think say the strongest theoretical boundary now we have is the Hammersley-Clifford type theorem for the composable graphs. So that's taking us a while. It seems to be, I think what encourages as well, why it seems to be a natural notion is that it seems to work as well for Lévy processes, for instance. So if you're familiar with Lévy processes, they are characterized by, you can also characterize them by the Lévy measure of, say, when you stop the process at any time point, or when you look at one specific time point, say the Lévy process at time 1. So we know that, I mean, it's long known that they can be decomposed into Gaussian parts and remaining jump parts, even though that isn't quite unique how you can do that. But there are promising results as well by Jeff and Sebastian in his postdoc that they also decompose Lévy processes with respect to exactly this kind of notion of conditional independence. And so if you decompose that into the jump and Gaussian part, for the Gaussian part, conditional independence is also quite well known. So it's encoded in the precision matrix. And for the jump part, conditional independence is encoded via this notion, basically. And it seems to really work very well that actually the so even with the probabilistic notion of the Lévy process, if you have a multivariate Lévy process, it decomposes the conditional independence, decomposes exactly in this way. That's also another thing that's forthcoming. I think they're going to publish that soon as a preprint. So it seems a natural notion that it goes beyond this kind of extreme setting, which we found quite interesting. So it doesn't matter whether you consider it in this direction where I've been coming from the extremes direction, or from other notions where you have such Lévy measures appearing. So I think in principle you could apply it to any kind of setting where you have a semi-group structure, although that may practically be not so interesting. I think from practical point of view is either you look at extremes or you look at some stable, but I think from practice point of view probably wouldn't look very much at other kind of semi-groups. But for these two, it seems a promising notion. And so another point that isn't essential is because we don't need homogeneity. And this means we can also extend this to measures that, say, in the extremes world would embody something that is called asymptotic independence. So we wouldn't have to deal with homogeneous measures. You can ditch homogeneity and have this also in situations where that's just for the experts, but where the chi measure is essentially 0, but you have the eta coefficient taking over. So that even in these situations, you can now construct such graphical models. We have one example in the article preprint, but I guess this would by further time to explain it. I think I'm going to stop here and hope that some inspiring part at least is in it. And so thanks. Yeah.
So very nice. The graph, so what about city graphicals? How about graphicals?
Yes, good question. So it seems less natural to look at. I think it often doesn't hold, even if you have semi-graph. Semi-graphic seems to be good. I think it's. I need to remind myself again, because actually after 1.5 years we just got the first reviews back, so, and the same question was appearing as well. We talked about it 2 years ago, and I can't quite remember anymore why we didn't follow that up. I think it didn't work. So, but I have to look into that again. That's a really good question. Yeah. Yeah.
Graph or then you can extend all graph.
Yeah.
Other people
Yeah.
on their graph.
Yeah. So we needed that recursion basically for the composite graphs in order to prove it. So I'm not sure if you can do it without it, but it would be nice. Yes. Yeah. Yeah. So thank you for the question. Yeah.
So I'm not a specialist in this, so what I took from that is that it's a really interesting way to try and understand a bit more about how to think about potentially modeling dependencies and extremes. The mathematics is all done after on a measure where basically in applications you've conditioned on things being right. So that's the kind of asymptotic measure. So I'm shouting pardon to it. Am I right in thinking then that basically all of the non-extreme observations that you would have in an application are kind of gone down the book on, but is the origin?
So I'm not sure if I fully understand the question, but
I'll phrase it
yeah. So yeah.
Is the organ that we're looking at the organ corresponding to all variables simultaneously? True.
So they don't have to be simultaneously extreme because we have mass on the faces through the origin, basically.
On the axis.
So we can't have mass on the axis all the time.
Okay.
And so mass on the faces through the origin. So it is perfectly possible that not everything has been.
Right,
Yeah.
okay.
Yeah.
Because you were kind of a lot of the presentation you were kind of excluding. Okay, you were excluding the origin, but not necessarily the axis.
The axes are precisely all the time. They stay in the model. So we're looking now at models which have mass, say, only focus on upper opposite. They can have mass here, if you were in threshold study, and also everywhere here. So you can have, yeah, that's basically what we need to keep in the model. And it can even be the case that we have only mass on those bits.
Right, okay.
Yeah.
Because I was thinking.
This is precisely characterizing asymptotic independence, say, between those components where, yeah, so if we only have mass in these kind of places, that would be the case.
So that's going to be critical for doing real data analysis.
Yeah.
Otherwise, the versus dimensionality is going to benefit from data.
Yeah. This is exactly giving us also the independent components. So you could also think now if you have different parts of the kind of combining these of some kind of random forest situation somehow, so that you have some things that get your mass only here and then mass only in the independent parts. So yeah. But they're going to be, I suppose, identifiability issues. So also once we get into the asymptotic independent modeling part. So it's because now we have different ways how to define those graphical models and how to encode asymptotic independence in them. So it's, yeah. Then it depends probably on the application for which kind of model you want to go. So, and how much sparsity you want to enforce. So, yeah.
How exactly is this being also?
So at the moment, I mean, maybe I can go to some situations where it's been looked at for structure learning among extremes at the moment. So, for instance, here is the river Danube, and you can look at the flow speeds at different locations. And this is where it's been used. I mean, this is just the overview of the situation, but this is one of the, I think, because so many data are available, is one of the benchmark graphs in the setting at the moment. This is a decomposition that was in the first paper, the JSP paper, and here the statistical inference focused on having block graphs in the end. So this is the structure of the stations that the river gives you, but at the same time, this is the inferred structure, and there are connections between some of the other variables, probably because you have meteorological systems also influencing how much flow speed you have. And so depending on which catchment or valley you're in, probably you get the same kind of weather system, and it's not only determined by the kind of connection of the river itself. So so this kind of example has been used in some of the other follow-up papers as well. So I think this is also the same network where estimation has been carried out. So airport delays is another example where it's been structural learning about. So for airport delays, is typically the extreme delays that are mostly of interest again. So the average delay is probably relatively small, but so here we also carried out the analysis of underlying graphical structure in the extremes between airport delays, how they are connected to each other. And that could also help to understand how these delays are interconnected with each other, where to put resources, or how to address this better, perhaps.
You're trying to essentially read-on your view of this problem. And once you read off the conditional dependence, how can you use that to draw? Okay, to give an example.
Okay.
Conditional dependence. It's like when we can simplify your probability by more basic statements. It's how one can use. Whereas in this case, how to use the derive.
So in this case, it is a model for the thresholds. So you're right, you're not modeling the boundary distribution. There is literature about mainly Johan Siggers, who has been working under dominant fraction conditions and proving how conditional independencies in say from the non-limiting models transfer action to the limiting model, like you see here. You're right to say this is only a model for the extremes, and where you have conditional independent structure in the sense of but it's not the same as that. Yeah. So basically, one sorry. So one part where we started to incorporate, when we started to incorporate conditional independence directly in the models, in the probabilistic models, we failed. And this is how this direction has emerged. So I'm not sure if that answer was satisfying enough, or it fully answered your question. I'm happy to also talk about it. So,
yeah. Okay, so we'll thank Kirstin one last time. Thank you. You're invited.
Thank you for the okay, so
Okay.